Yeah. That's fine. Oh, hi. I need to wake up earlier. Oh, you can hear like no one. Wait, which one? Yeah. Ah, they refinished. Yeah. Yeah, I forgot.
Actually, I'll probably show something now.
We have the t-shirt design. Oh, that one got conferences. Yeah, so we make her.
Are you ready? All right, well, welcome back to the second day. It was definitely a very exciting day yesterday for the Mock-up. There's a massive conspiracy to take out 75% of the lecturers and 50% of the organizers, as Miki is going to tell you now. So,
Yeah, some of you may be wondering why several lecturers and organizers irresponsibly didn't show up at the poster session yesterday. And I could have come up with a better reason, such that we were zoomed into the meeting with National Science Art Council. No, but we got stuck in the elevator on our way to the 11th floor. And now, as old joke goes, how many theorists it takes to change the light bulb? The answer is 3. One is holding the bulb, and the 2 are rotating the table. The first one is standing on. So how many theories it takes to stop the elevator? 7. So it all went well. If fire fighters came to our rescue, and this is the finale. You see the fire engine at the background. So that gives something to talk about, I think, until the rest of the day. All right, so that's why. Now I can now switch to the Blackboard. Okay, you again have me. We talked a lot about Boltzmann equation in its simplest form, and I put the fear of God into you against using RTA approximation, at least without thinking about it. I think we settled on this. Then, in a bit of a brushy manner, I started to talk about Kubo formula, which is supposed to be much more general. Well, we're only limited by linear up response, but in principle, we can take into account all interactions that we want. Okay, and I sketched a formula for the conductivity, which would be now static conductivity, and temperature will be equal to 0. And then it has a rather simple form before we do the averaging. I think when I spelled it out last time, I skipped the imaginary part of the Green's functions. So R stands for retarded. And then we have the derivative dr, say alpha, dr prime beta, and then there's an integral over r prime. Well, of course, there is factor of e squared, and for parabolic spectrum, you have the factor of the mass. So R here, for those who haven't dealt with this, so there are two types of Green's functions, retarded and advanced. And they differ by allocation of the poles in the complex plane of the frequency. So here the imaginary part is coming from, let's say, elastic scattering, and it is always the single particle time, which is just the imaginary part of the self-energy. And now this is supposed to be averaged over this order. And there are two things we do in order to make this work. This is so far this exact, but totally useless, right? So we developed the perturbation theory with respect to disorder, saying that the Green's function, which describes a process of propagation from one point to another point, will acquire potentials somewhere in the middle. Okay. We plug this in, this infinite series. And we get two types of diagrams. In the first one, the potential points belong to the same arm of our bubble. When we do averaging, averaging means that I have potential here at point R1, potential here at point R2. I take an average, this becomes a correlation function. And if I continue with this kind of insertions, sooner or later, to whatever order I'm going to do it, I will form an exact averaged over disorder Green's function. So let's say that I'm continuing with something else. And then at the end of the day, this all sums into the peak. So this is disorder average Green's function. So this our contribution, because the Green's function only knows about the single particle time, I will get quasi-conductivity from here, which will look like transport time is actually the single particle time. Okay. And if I have isotropic scattering, point-like impurities, this is the end of the story.
Can I just ask about this?
Oh, sure, yeah.
So, but what, this guy is not averaged, so if I just use this Green's function without the thick lines, I'll get this result. So there must be.
Oh, so this is average. So once I get this dashed line, it means that they took two random potentials and they averaged over
No,
this
I
order.
understand, but that's not what I'm asking. So if you didn't do this impurity averaging, you simply computed conductivity, this one bubble.
Right.
From that Green's function.
Yeah.
Which is not disorder averaged.
It is.
Oh, it's already.
Yeah, sorry. Yeah. So I cannot write down the non-disorder averaged Green's functions
That one?
because it's random. You know, it's
Okay.
it's an object. Yeah. So this. So this is going to be the thick line.
And also, is there can you just have to work it out from like a layman spectral decomposition, or is there some intuitive way why it's only retarded this into the conductivity?
Oh, this is Lemon decomposition, our continuation, but it's retarded. But this is the imaginary part, and the imaginary and the retarded Green's function. The imaginary part of is the difference between retarded and advanced. So when you open it up, you will have retarded and advanced. So there is no preference. Yeah. Sorry, who was first? Okay.
Does it depend on the frequency or anything?
No. Well, we already said that external frequency is equal to 0. So we're measuring DC conductivity. Now there is also frequency or energy of the fermion, right? But I also said that I want to do the 0 temperature limit, which puts this R frequency to 0.2, right? Yes, at finite temperature, at finite frequency, so we know tau, that is function of energy in principle, right? Okay, so what stands here, if I do 0 temperature, it's tau at the Fermi energy. And if it's not 0 temperature, well, it's still Fermi energy plus minus temperature. So this effect is irrelevant for our purposes.
Are you going to talk about conductivities with interactions eventually as well?
Yes.
Okay.
Sure.
Then I will.
Sure. Okay. And then there is another, so why this is the full end of the story if we have isotropic scattering? Because if I try to do the averaging of a different type, when I have one potential point on the top, another potential point at the bottom, and then I do averaging, that means that I join these 2 points by the correlation function. Oh, sorry, I forgot you. Sorry. Yeah. It is related. You can write down the time moderate via the retarded and advanced. So there are 3, basically, Green's functions. You have Matsubara, you have time moderate, and you have retarded and advanced. Retarded and advanced analytic are continuations of the Matsubara from the Matsubara axis onto the real axis. Okay. Time moderate is you just choose different R combinations of the psi operators. Yeah, so you can do it in whatever technique you want. So what I usually do, I start with Matsubara because it's very compact, and then I do analytic R continuation, and then you immediately end up with retarded and advanced Green's functions, which are convenient to work with because they have fixed positions of the poles. Okay, so if I put in a correlation function here, but for isotropic scattering, this is a delta function in real space, which means that in momentum space, it's a constant. And then in momentum space, I have some momentum k in here, same momentum k in here, but after the scattering, I will have momentum k prime and momentum k prime, right? Now, you have also velocity here. Well,
Why is it K? K and K is supposed to K minus Q?
because it's conductivity at 0 wave number.
Q.
Yeah, 0 wave number. Right. So then this K and this K are the same. I also have the current vortex, which came from Fourier transforms of the derivative here, which is the current operator, which means that I'll have another factor of K here. So this K here is odd, of course, in K2 minus K. The Green's function here knows about the momentum only via energy. So if I have an isotropic system, actually, forget it. As long as I have time up reversal symmetry, epsilon of k is equal to epsilon of minus k. So each of these Green's functions is an even function of the momentum, and here I have a vortex which is odd. So this part of the diagram vanishes, or likewise, this part of the diagram vanishes. So for point like impurities, this is the end of the story. We don't have any other.
There's an
Yeah,
integral sum over k and k prime.
Yeah, so this line in principle is a function of k minus or k prime. But if it is a constant, it is not. So this line kind of dissects the diagram into two parts, which are independent from each other. Okay. All right, but in a more general case, let's say we do averaging of this type. And let's say starting from second order, I can think of three diagrams. Which have very different physical meaning. And the workhorse of semi-classical transport is this diagram being summed up to infinite order. This is the ladder diagrams. This diagram is the first diagram in the sequence which leads us to uplocalization. And these diagrams were kind of ignored because they're neither nor. But it turns out that the resistive anomaly, which we still have as our goal, we need to take into account these no-name diagrams. All right, so what's the difference between the three? So first of all, there is a small parameter in the theory, otherwise any perturbation theory doesn't make sense. And the small parameter of the theory is that the width of the spectral function due to impurity scattering is small compared to the Fermi energy. So we still have well-resolved quasi-particles. The width of the spectral function is 1 over tau single particle, and so that has to be much smaller than the Fermi energy. Sometimes we just combine it like this and say that this is a good metal condition. Okay. So that's the only parameter in the theory, and mind you, this is a single particle time which stands here because it comes from the width of the Green's function. Transport time is something that we get at the end of the day. This parameter makes our life much simpler for two reasons. First, as I just answered to Leo, when I open the imaginary part of Green's functions here, I will have products of type retarded into retarded, advanced into advanced, but then also retarded into advanced. Okay? They have very different properties. If I take a product of GR, I will have to integrate it over momentum in a d-dimensional space, right? And in general, it's not a zero, right? But now I'm going to use an assumption that the spectral function is a very narrow function on the scale of the Fermi energy. And that means that all the action is taking place in a narrow interval near the Fermi energy. And then I don't need to integrate over the entire momentum space. What I will do, I will integrate over the quasi-particle energy, which is the actual energy minus the Fermi energy. And if I formally do this transformation, I will end up with this. This is the solid angle with momentum k. This is the full R solid angle. And you certainly know that I will have the limits from minus Fermi energy to R plus infinity. I didn't gain anything. But now, because I want to say that relevant range of psi k is small, I will extend the limits of integration to plus infinity minus infinity. And I will also take out the density of states at the Fermi image. And then the integral over the quasi-particle energy becomes a one-dimensional integral, which is analogous to the integral over the frequency. Now, if I have the Green's functions of the same analyticity, meaning GR, let's say two of them, this integral is zero because it has poles in the same half plane of the complex plane. So products GR and GA for the same reason, when we integrate them over quasi-particle energy, they vanish. Products of RA type survive because the poles are on the opposite sides of the real axis. I will get n on zero up result. Okay, that's
I
what.
thought they also vanished because of, you already made an argument because of the time reversal invariant.
No, so this is only isotropic scattering.
Oh, you're not doing the general case.
Now I'm doing general.
I know one is. Isn't angular integration included in the definition of that kind of thing?
No.
That's for states. We go from state K to the energy.
Like, let's do it in 2D. dkk d theta over 2 pi. So density of states come from the transformation. Yeah.
That's
open.
okay.
Yeah, but that's why I divided it out by the solid angle. Yeah. All right. Yes.
You started with GR, then how did you get GA or the cross product?
So this is imaginary part of GR, right in here. An imaginary part. So GR and GA on the real axis, they are complex conjugate to each other. So the imaginary part is just the difference between GR and GA. So you stuck it in here, you will get all types of products. So then in our diagrams here, it will be always like this. On one side, we have R. On the other side, we have A. Why we have R into R? This is elastic scattering. It doesn't change the energy. So analyticity of the function will be the same.
It never, that's what you can switch.
Only if you have inelastic scattering. Elastic scattering is the same.
But that relation, that one, does that hold also with the disorder average one? Do I not need for that one to have just plus or minus I times 0?
Yeah, so but for ideal, yes. So you can do this exercise with ideal Green's functions in the absence of a disorder. Then your result will be that the conductivity is a delta function of a frequency.
No, but I just mean the relation that imaginary GR is GR minus GA.
Oh, yes. So this is totally general. Totally general, and this is valid before the averaging. It's just the property of analyticity. Yeah. On the real axis. So if frequency is on the real, then this is true.
Why this energy conservation scattering means that R continues to stay R along the branch?
Let me give you an answer in the Matsubara language. Okay. Suppose that I come back to Matsubara and I have some frequency omega m in here. And because the scattering is elastic, I will have the same frequency here. Okay. So then when I do analytic R continuation, they continue into the same type of frequency. Right? Yeah.
So should I think of these lines, that's at least for first diagram, as already the thick lines with disorder average?
You can. You can.
Otherwise, there'd be 0 plus and 0.
Yeah. Yes, we can do it in this way. We can first take into account all self-energies and then start dress up at the vertices, but it doesn't really matter, which order we do it. Because this is all being summed over. Now, why do we want this diagram? to be the working force. This is related to the phase space. I have momentum k because this is zero wave number R conductivity. I have the same momentum k. Let's say I have momentum k prime here, and then momentum k double prime here. And there is some momentum R conservation, so the line takes whatever they need to take in order to specify a momentum R conservation. Now, because of the same condition that I'm only interested in the narrow interval of energies near the Fermi energy, I want all electrons here to have their momenta close to the Fermi surface. Right? Okay, and here I have three independent momenta, so I can project each of them independently from each other onto the Fermi surface. Let's look at this one. I have k prime, k double prime. This line takes k minus k prime, so I have k minus k prime plus k double prime, and then k minus k prime plus k double prime k. Okay, so how many fermions do I have? Well, now I have four of them, right? Five. So I have k, I have k double prime, but I also have the fermion with momentum, whose momentum is a combination of the momentum of other fermions. So if I project k onto the Fermi surface and k prime onto the Fermi surface and k double prime onto the Fermi surface, it does not guarantee that the momentum of this R fermion will be also on the Fermi surface. I need to impose some constraints. So for example, I have to say that as a vector, k is very close to k prime, or k prime is very close to k double prime, right? So in other words, in this diagram, I'm free to choose three independent momenta without any correlation between them, and they will be all three onto the Fermi surface. But in this one, I have to choose two momenta to be close to each other, and then the third one is doing whatever it wants to do. And that means that the phase space of momentum integration is going to be small. And because there is only one small parameter in this game, it's all going to be small by same 1 over Fermi energy tau singularity. Okay. Same is true about this diagram. So there is also one R fermion with momentum, which depends on momentum of other fermions. Okay, so then what we do for semi-classical transport, we forget about these across guys, and we sum up the ladders. If we do this, this is an exercise shown in other notes. All it does, so the sum of these diagrams plus the diagram without vertices will give us a conductivity which will look almost like this one, except for the single particle time will be replaced by transport. Which means that this diagram will first cancel this diagram entirely, and then I will replace it with the transport time. There is certainly a special role of these diagrams. Why? They're small. They're small in this parameter. However, if we calculate this diagram carefully, and then we go to next order and draw a diagram of the same type, which is called maximally across diagram, the result of the next order is not going to be smaller than the previous order. It's just going to be equal to the previous order.
How does it compare to those?
The
transport.
Transport one, small.
This is smaller now.
Sure, yeah, so this is smaller than this, but this one is not smaller than this.
It's smaller by that same parameter.
Yeah.
Because there's the same constraint.
Yeah, there is some
Just there's
constraint.
No
Right.
more constraints.
Right, no more constraints. But it means that if we presum the sequence of these diagrams separately, we'll end up with a divergence because the series will be 1 plus 1 plus 1 plus 1. Okay? So although these diagrams have small prefactor, 1 over Fermi energy tau, we have an infinite sum. Yes?
What is the left side? It's 0. 14 K the double prime.
Why is this diagram is not 0?
Yeah.
It is 0 for isotropic scattering. No, by doing other general case. Yes.
And that's why you get
Transport.
SP is the same.
Yeah, so if it's isotropic scattering, tau SP is equal to a tau transport, we're done at this level. Yeah.
Probably big basic, but in calculating the single particle self energy, we already dropped some diagrams that were down by 1 over EF tau single particle because of the same kind of constraints, the cross diagram.
I didn't tell you what 1 over tau SP is. I could sum all diagrams for the self energy, however I wanted, and call them 1 over tau SP. So I didn't use, let's say, Abort approximation.
Is the second and third class of diagrams be more instant to name them together?
Interacting systems, yes, but this is still single particle. Yes. We did disorder averaging, right, which a priori translational symmetry. Yes. No. No. This would be the Aslamazov-Larkin type diagram. One of them, let's say. Okay, but I can change analyticity here because this is elastic scattering. So my retarded will go into retarded, back into retarded. So I'll have product of retarded Green's functions. And this is 0 by the argument that the poles are on the same axis. When this becomes an interaction line, I can have this being retarded and this advanced. Then this is non-zero. I'm sure I saw more hands, but probably they help. Okay. So what it is, it's a mathematical manifestation of tendency to Anderson up localization. How do we know this? Well, we can certainly calculate this, assuming that now so now we have to deal with this divergence, and at the level of what I told you, we have only 2 ways to cut it. I can either restore the finite frequency of light, and then in 2 dimensions, I will find that the sum of these diagrams the infinite sum of these diagrams, which is called Couperon, denoted by this, meaning that I summed all maximally cross diagrams. Yes, it gives a small correction by this parameter, but it comes with a log divergence. And if I choose my frequency to regularize it, then it's going to blow up as a log. And it's going to come with a minus sign, which means that my conductivity is going to be suppressed. And literally speaking, if I go to 0 frequency, my conductivity would vanish at some point. Of course, perturbation theory breaks down, but it shows the tendency towards Anderson up localization, which in 2 dimensions, in marginal adimensionality, is always there for any strength of disorder, right?
What is the way?
It's a frequency of light, which I had to restore in order to avoid the divergence from summing all ones. Or I can restore the finite system size. That's another cutoff. Sorry? Magnetic field will help me a little bit. I will kill first loop. but the second loop will be still divergent. However, what is done in practice when we measure DC, we invoke dephasing. That is the inelastic processes which change the phase of other electrons, and we stuck it into the Cooperon, saying that now it's not a massless bosonic propagator, it has finite mass, and this phase breaking time will cut our singularity.
Why is this called a Cooperon?
Because this is incoming, this is incoming, this is outgoing, this is outgoing, so it looks like a Cooper pair.
Particle channeling just
Yeah, yeah. Or you can, yes, you can take this diagram and you can untwist it so that now the arrows will be parallel to each other, and then it will look like ladder, but in the particle-particle channel. But it has nothing to do with formation of Cooper pairs. But there is some physics in there. There is a beautiful hand-waving picture of how you can obtain weak localization corrections by considering time-reversed path when electron starts its motion in the presence of disorder, and then there is kind of a fork. It can go along the same path counterclockwise or clockwise, which means that these two trajectories are the time-reversed copies of each other. And localization results from the constructive interference between these two paths. That's why the conductivity is suppressed, because the interference between these two paths lead to enhancement of return probability to the original point.
And there's a disorder ladder along that band, right, between the two lines.
This is not a diagram. This is,
But
yeah,
I'm saying that looks like that.
this is just a trajectory in real space.
But you can, that diagram,
Oh, this
I'm
this
saying-
diagram, yeah.
that diagram looks like that real time, real space.
It's a maximally entangled diagram in the sense that you start to scatter at one impurity, right? You haven't done, you're not done yet, and then you meet the next impurity, and then you're not done yet, you meet another impurity. So this is maximally entangled scattering process.
this 2D result.
This is 2D result. Yeah.
3D.
In 3D, you will have a correction of order Fermi energy tau, okay, which is infrared stable. But if you look at the, for example, the frequency dependence, you will find that this is non-analytic. So there is a signature. And then when this parameter becomes of order 1, you can boldly claim that this is where the real Anderson transition happens, because in 3D you need the threshold.
Do you see it from there? Like,
Well, this is a perturbative R calculation. So strictly speaking, you have no right to put this R parameter to 1. But if you do it, you will feel good that at least it gives some phase in the numerical R calculations. No. Of course, yeah. You can cheat, but you can cheat only that much, right? So the real information about Anderson localization comes from numerics. Yes.
Here, it's equivalent to the imaginary part of the target or something.
Okay. After I discarded the products of retarded, advanced, all these diagrams are going to be made in the same way. Upper line has only retarded Green's function, and the bottom line has only advanced Green's function. For disorder. Okay, so weak localization, strong localization. Oh, sorry.
So you said something about finite system size. Is that the same as doing finite Q, or?
Yeah. Basically, yes.
Okay.
Yeah. Well, not external Q. Okay, fine. Yes.
Okay.
Yes. Finite, very small, but finite external Q. Yes.
Just to be clear, in this diagram, the two fermion lines are in the same direction. The arrows are in the same direction. No,
Which one? 1, 2, 3?
or they're in different directions.
Yeah, opposite. They're all particle hole. They're all particle hole.
The process suppressing the increase magnetic field.
Yes. Yes.
Does that for the
The Green's function becomes a matrix, a tensor in the spin space because you break the time reversal symmetry, right? So G up up is not the same as G down down. Right. This is something which I'm not going to talk about. This is so now probably this is a point kind of to overview and ask what the Boltzmann equation that we started with can do for us. It is totally equivalent to a version of the Kubo formula where we sum ladder diagrams. For all purposes, we can calculate whatever we want and we'll be getting the same result. Boltzmann equation cannot describe quantum coherence physics. And it's not the fault of Boltzmann equation. It wasn't done this way. If you cannot split a log with a screwdriver, it's not a fault of a screwdriver. You need to use a different tool. Okay? So, but there are other diagrams, such as this one, which become important under certain circumstances, and Boltzmann equation also fails to reproduce them. And this is a subject which is probably going back to 19th century. And it was looked at over the millennium, on and on. And this is known under the name of classical memory effect. What is classical memory effect? Well, I'll give you a solid example, but let me tell you one hidden assumption about Boltzmann equation. It assumes that the scattering process is Markovian, which means that the memory about collisions in the past is lost by the time you start to do a new arc collision. Okay? Very subtle arc condition. And there is a good model, fortunately exactly soluble model, which showed that this condition is not always satisfied. The model is called the Lorentz model. And it exists in two forms. So one can think of a gas of hard spheres or hard disks with collisions between them. Or one can fix positions of spheres or disks in real space and have one projectile going through the system. It's a pinball machine, right? So let's choose this simulation. So I have spheres or disks, they're fixed. And then I have a particle which scatters of them. Now, we can treat the same system via the Boltzmann equation. Well, we know how to calculate the transport time for, let's say, hard sphere, right? Then we plug it into our Boltzmann equation, and we can also calculate conductivity if this projectile particle is charged, right? And we can calculate the something which is related to the arc conductivity, which is velocity acceleration function. Meaning that I prepare my particle with some initial velocity v at time 0, then I let it go, and then I'm asking what's the overlap between the velocity at time t and at time 0. And the way Boltzmann equation is built, you have first order time derivative on the left-hand side, and then you have minus f over tau on the right-hand side. You're bound to have an exponential decay. So at long times, much longer than tau, I wouldn't specify the index, the acceleration function will decay exponentially. Okay? And if we do Fourier transform of this, we will recover a familiar, and we take the real part of this. We'll recover a familiar Drude-like dependence on the frequency, and velocity for charged particles is the same as our current current, so this is going to be Drude-like our conductivity. Okay. And the exact solution, which was worked out in the early 70s, doesn't show this. Or more precisely, it shows that there is an initial decay, which is exponential in time, but then it's followed by a long power law tail. And so the exact model, the exact solution, tells you that long time behavior of the velocity correlation function is actually power law, d being the spatial adimensionality. Okay. Now, if we Fourier transform this, yes?
The exact solution of the Boltzmann equation without any relaxation time approximation or anything like that.
Yes, because these are hard spheres, we can use whatever version. Yes. Yeah. No, so this, okay. This is Boltzmann. This is Boltzmann. This is the exact solution of the Lorentz model, which is not done by our Boltzmann because you will have the same.
Well, I guess the question is, how do you know you have the correct collision interval, the Boltzmann equation?
We figured out what it would be, right? We know that this is F average minus F. And spheres are isotropic scatters, right? So we know that the right form is F bar minus F. Over tau, we calculate tau for a hard sphere. So there is really no ambiguity anymore. And we also figured out that if we talk about conductivity, right, and if we pull the particle by a weak electric field, it doesn't matter what we use here. So the exponential is coming from this term. I have df dt. So if I do time-dependent problem, I have df dt on the left-hand side, and I have f over tau, bound to have an exponential. So if we do Fourier transform of this power law tail, then it will give a non-analytic scaling of the Drude conductivity. It will start with a constant, of course, which is the residual one. And then it's going to be plus absolute value of frequency to the dimensionality d over 2. So mod omega in 2d, 3/2 in 3 dimensions. So that's a big change, right, compared to the usual picture. If we think about the low frequency behavior of the Boltzmann kind, our conductivity, it's bound to be analytic. So we start with terms which is omega squared. In 2D, we start here with mod omega. Also, pay attention to the sign. Here, the conductivity is going to be suppressed by finite frequency. Here, it is enhanced. Okay. Where is it coming from? Well, because my scatterers have finite size, and this is very important. It wouldn't happen for point like R scatterers. But because my scatterers have finite size, I have finite probability to come back to the same scatter several times. And this is anti-classical memory effect. And the prefactor of this power law is large in proportion to the size of the scatter. So the bigger the scatter, the larger is the probability to come back many times. This effect is amplified in the presence of magnetic field. So if I have now magnetic field, by itself, it has a tendency to curve electron trajectory and making electrons go round and round, right? So it increases the self-return probability up to the extent that if in 2 dimensions, I have hard disks, and if the field is strong enough so that the trajectory is a rho z bound to a particular disk, the conductivity goes down to 0.
Can you understand this without as an average of a distribution of taus, parallel distribution of taus. Somehow it's not, those that get trapped have a very long tail.
You can get this result, I believe. I haven't tried, but I did something else. If you say that your disorder is not simply scattering probability, which is already averaged, but it's actually a random force on the left-hand side of your Boltzmann equation. And then you solve, quote unquote, exactly the Boltzmann equation for a given realization of your hard spheres, and then you average. Yeah. Yeah. Yes.
Is there a significant difference between 2 dimensions and higher?
I'm sorry?
Is there a significant difference between 2 dimensions and higher? Meaning that the random walk is guaranteed to occur?
Oh, yes, it's stronger in 2D. For example, the non-analytic part of the conductivity is mod omega in 2D and mod omega 3/2 in 3D. Right. So yes, there is this.
No different singularity except for the power.
Yeah. And so let me come back to this. So it means that, for example, the conductivity of a two-dimensional system, classical system, nothing to do with our quantum Hall effect, is 0, but precisely it vanishes at some particular value of the field when this orbit does not touch the other disk. Right? Now, there is one more property of the Boltzmann equation, which I didn't tell you about, but it's in the notes. It's about magnetic resistance. The statement is that as long as the system has isotropic spectrum, doesn't matter, parabolic, Dirac, or whatever, then it has magnetic conductivity, it has Hall conductivity, but there is no magnetic resistance. The resistance in the magnetic field is the same as the resistance in zero field, and that comes about mathematically when you invert a 2x2 matrix for the conductivities, the field dependence drops out. Okay? Experimentally, this is definitely not the case. We have systems now, a lot of them are almost isotropic. So these are two-dimensional electron gases, these are three-dimensional Weyl and Dirac metals, etc. Because they are low-density systems, they are almost isotropic, yet they show extremely strong non-linear, linear, almost linear, non-saturating magnetic resistance. Right? The Boltzmann equation will tell you that it's absent. So we have order of magnitude strong magnetic resistance in the experiment, and theory based on the Boltzmann equation give us flat line. Theory which takes into account memory effects does produce a magnetic resistance. It doesn't have this flaw of canceling the field dependencies. So this is important and probably somewhat overlooked because there are not that many studies of the classical memory effect.
What's the original reference for this?
It's in my note.
What year?
Oh, 1971. This particular result.
What's the author?
German name, Ernst. I'm not sure that this is the first because it started early in the 60s, but this kind of is solid statement. Yes.
I think I have missed the point about what's non-Markovian here. So if I was just doing a random walk in some random environment, I might get stuck in some places for longer amounts of time than others, but it's still a Markovian process.
Well, if you're really jumping from point to point, then the probability to get stuck is measure 0 because it's a point. Having finite sizes increases this probability. Just because, by surface area argument.
Getting stuck doesn't mean that it's non-Markovian.
Getting stuck, it does mean that it's Markovian because once you get stuck, the memory about this scatter is always there. You don't lose it.
This is upon disorder averaging, it becomes non-Markovian because you sort of know the fact there is a scatter in this specific point.
Well, yes, disorder averaging. Yeah, so we can talk about.
If I look at specific disorder realization, this is a Markovian process.
Yes. But after averaging, yes. So we need to look after averaging.
What's the thing that's averaged?
Oh, correlation function.
You think that correlation function can't be reproduced by a Markovian process? Like once you just sort of average.
This correlation function cannot be reproduced by a Markovian process, or you need to take, okay, there are non-Markovian processes with memory, right? So you can probably write down a Langevin equation. There should be a non-local entire memory term. It's called, escapes me the name, Zwanzig. Zwanzig, and there is another name, More. Yes, More, Zwanzig More.
The constant piece of that, just the Drude up to the time scale, like that tail only happens at long times.
Mm-hmm.
So the constant piece has a form of a Drude, or
You know, no one really knows.
what?
No one really knows.
But that formula, that power law holds on time scales longer than tau.
Yeah. Yeah. Well, actually, yeah, longer than tau, but so let's say I have a correlation function of a disorder with some length psi. Then this is where you see this power law or singularity, right? All right, so that brings us to the subject that I wanted to talk about. Originally, I think we have almost all preps for that. And the subject is the resistive anomaly, which I'll pack in such a way that you'll probably understand why I tortured you for so long with scattering by impurities. I'll have to say just a couple of things about phonons, just to make sure that everyone is on the same page, but this is going to be largely unimportant. Okay, so what's the resistive anomaly? You measure the resistivity of, let's say, a ferromagnet of nickel. Yes.
One of the Barnes model with power law indicating correlation and both of them. Yeah. This is what they feel like.
To diffusion. Well, so here we're looking at zero wave number correlation function. So the diffusion by itself doesn't show up. If I would measure the current correlation function at finite q, then I will see that there is a diffusion pole. Sorry? Yes, also in Lorentz model. Okay, so let's say this is nickel, and then the anomaly looks like this. It's an E at TC, and TC is 625 R kilo. High, right? Now, the first theoretical attack at this issue was by two giants, Jean and Privel, 1958, who basically formulated the problem in terms that I'm going to use. They said, look, we are at high temperatures here, right? High compared to what? Okay, here I have to say a couple of things about phonons, right? So if we didn't have a ferromagnetic transition, this would be the region where the resistivity is limited by electron phonon scattering. Moreover, this is particular regime of electron phonon scattering, which is called either equipartition or quasi-elastic. When scattering of electrons at phonons is almost elastic. Why is it so? Well, so first of all, how do we define this? There's a temperature which is called Bloch-Gruneisen temperature, not to be confused with other Debye temperature. They're in general different. And above this temperature, you are in the equipartition regime. Below this temperature, you are in the inelastic regime. So what's the meaning of this temperature? When electron scatters from a phonon, typical momentum transfer, which is significant for conductivity, is of order RKF. So we use phonons with wave number of order KF. For historical reasons, we put factor of 2 in here. But as Steve said yesterday, this is just order of magnitude estimate, but we do it for fun, right? Okay, now phonons, let's say if they are acoustic phonons, the frequency of such a phonon is speed of sound times q, 2kf times speed of sound. This is the Bloch-Grünen temperature. And what it means is that if temperature is larger than the temperature of phonons, I have plenty of these phonons. I am in a classical regime of the Bose function. And the Bose function in this case is linearly proportional to temperature, and the linear in temperature resistivity comes from this one. Right? So why it's not the same as a Debye temperature? Well, it is, but only in good metals. In a good metal, I mean high number density, 10 to 21, 10 to 22, the Fermi momentum is the order of the universal lattice spacing, and then speed of sound divided by lattice spacing is the same as the Debye temperature. So in good metals, Bloch-Grünen and Debye are the same. Okay. In low density systems, KF is much smaller than the universal lattice spacing, and then the Bloch-Grünen can be as low as 10 Kelvin. So if we have, for example, in graphene, linear anti-resistivity going down to 20 Kelvin, as it is observed experimentally, there is no reason to claim that we have a new kind of non-Fermi liquid. It's just plain old electron phonon scattering, which goes down to low temperatures in this case. So
below this temperature, you don't have enough phonons.
You don't have enough phonons, you have to use thermal phonons. And thermal phonons have their wave numbers smaller than RKF. Scattering becomes ineffective, and that's why you have T5 in other resistivity, because it's a small angle scattering. Okay, why the scattering is quasi-elastic in this case? Well, here is your electron, typical electron. Let's say it has energy above the Fermi energy for the temperature, right? There are plenty of phonons with momentum of order RKF. That means that a momentum relaxation is very fast. It's basically one strike. It takes one phonon to send the electron back. But the maximum energy that the phonon can take from the electron is TBG. And TBG is much smaller than our temperature. So what happens with the energy of the electron? It starts to diffuse along this one-dimensional axis. One can calculate the energy diffusion coefficient, and energy relaxation will happen on much longer time scale. Okay? That's why it's quasi-elastic. Not really elastic as are for impurities, because energy relaxation time is finite, but it's much longer than the momentum time. There are two interesting consequences coming of this. Now, we all probably heard about Wiedemann-Franz law, and the usual law is that Wiedemann-Franz law is the signature of Fermi liquid. Not really. Wiedemann-Franz law is the signature of elastic scattering. Okay? And when we think about elastic scattering, typically we think about low temperatures. And then if we take a copper at very low temperature, we measure thermal conductivity, we measure charge conductivity, form the Lorentz ratio, and we get the other universal number. But then if you think about history of the effect, Wiedemann-Franz, this is 1857. They couldn't work at helium temperature back then to measure the residual resistivity. They had two temperatures, room and ice. Okay, really. And by looking at these two temperatures of resistivity of copper and aluminum, they noted that Wiedemann-Franz law, as it's now known, is satisfied. Why? Because they were in this regime. They were in the regime of quasi-elastic scattering by phonons, which at room temperature is already pretty much satisfied in both our materials. Okay?
I thought it was also important that in like copper or something, the electronic velocity is much larger than the sound velocity. That's also important. So that, right?
If not, then you would not get into a quasi-elastic regime, right? Yeah. So of course, speed of sound, if speed of sound is larger than the Fermi velocity, then Bloch-Green-Eisen is larger than the Fermi energy. And then your entire temperature range before melting is inelastic.
Another question about this. So, is there like the resistance data in a strong field?
There must be. It's just that I don't know. But are you asking about orbital effect or spin effect?
No, the spin effect.
Okay.
Like, can you suppress this anomaly at this linear?
There must be, but I claim my ignorance here.
So this anomaly you associated with being TBG?
Oh, no. This anomaly is coming from magnetic scattering. But I'm just talking about the broad picture. What are the scattering agents in this range of temperatures? So one is phonons in the quasi-elastic regime. And because they are in the quasi-elastic regime, we can treat them as impurities, right? And because they scatter equally probably with equal probability at any angle, they're going to be point-like impurities. Okay? In addition, there is always some junk, real disorder. We lump them in with phonons, and this is going to form short-range disorder. Okay? So that's the main scattering part. Thermal plus quenched disorder, and because phonons give you linear NT, you have this variation with temperature, but we need to focus only on a very narrow region near ATC, when in all non-critical quantities, we can place temperature equal to ATC.
Why is it quasi-elastic? Because temperature is high?
Because temperature is high, because temperature is, yeah. So TBG is somewhere. Okay. One fun fact about this equipartition regime. So second fun fact. First was Wiedemann-Franz. Second one is when we were talking about the maximally crossed diagrams, weak localization. Where did it go? Went nowhere. Okay. So I told you that if we sum infinite number of maximally crossed diagram, that was take us to at least weak up localization. And of course, I had in mind the picture of zero temperature, right? Well, nothing is done at zero temperature. Let's say we're at finite but very low temperature. Then the condition for the weak localization to be observed is that the dephasing time, which is the time over which the phase of electron is disrupted, is longer than the elastic time. And at low temperatures, the elastic time is obviously coming from a disorder, and the inelastic time, or dephasing time, is coming from inelastic processes, which is phonons, and more relevant at low temperatures, electron-electron, right? And so the ratio of tau phi to tau elastic tells you how strong the effect of localization is at any given temperature. When we are in the quasi-elastic up regime, well, the absolute value of temperature for localization doesn't matter. What matters is how large is the ratio of the phase breaking time and the elastic time. We are in the elastic regime, right? So momentum relaxation is coming from scattering of these phonons. Phase breaking time is related to energy relaxation time, and this time is long. So in this regime, we have the same window for localization as at helium temperatures. So if we were able to measure very accurately logarithmic temperature corrections on the background of linear one, then we should be able to see the same logs and same physics as we see at helium temperature. Has never been seen because it's probably very hard, but the premise is there. Okay. So this was fun stuff. Now, so I formulated what's going to be my main source of a disorder. And for me, Dijen and Friedel already said that the additional source of scattering is scattering from localized magnetic moments. We all know that if we have a lattice, then lattice does not provide us with scattering. We have Bloch theorem. But now, if I have magnetic moments located at the site of lattice, and these moments are not ordered yet, then at the lowest order in magnetic scattering, without going into Kondo effect, we have spin flip scattering. And because spins are now random, this is this leads to momentum of relaxation. And near TC, the correlation function spin zero. It's very long ranged, right? Because this is second order phase transition at the Minfeld level scales space, q squared psi minus 2. Psi is the critical, correlation length of my classical phase transition. Now,
So thermally flipping like mad, right?
oh no, you have critical slowdown.
Okay.
Yeah, so we have critical slowdown. So spins are very slow. And this is why I'm going to treat them as another kind of a disorder. Also elastic. So this is going to be my long range disorder. And it seems to be very trivial just to add them up. Right? And ask what's going to be the answer. And that's what Friedel and Dijen did in 1958. Yes?
Here, is it the itinerant electrons themselves or from the?
No. So let's say we have kind of independent physics. We have some moments which live their own life, and then we have electrons which flow then, right? So it's not a Stoner or ferromagnet.
But they're in a paramagnetic state.
Well, they are near, so they are both slightly above or slightly below. Okay, so what did Dijen and Friedel did in 1958? They believed in the Boltzmann equation, as they should. And the Boltzmann equation tells you that if you have two kinds of a disorder, electron impurity 1 plus electron impurity 2, you have to add the corresponding collision integrals, right? And that leads to famous Mathisen rule, which means that the resistivities add up as they were connected in series, right? Okay. But doesn't need even to solve the Boltzmann equation. Everything comes out at the level of the Fermi-Golden rule. The Fermi-Golden rule is something that we'll need to look at carefully. Oh, so another assumption which they made, and I will also keep, is that long-range disorder, that is my spin flip scattering, is weak compared to short range. So I will simplify my task tremendously. I'll be looking only at the lowest order correction due to long-range disorder. Okay, so our expectation is that the resistivity should be proportional to 1 over tau due to short range, call it S, plus 1 over tau transport due to long range. So here it doesn't matter. Here, of course, I need to think about our transport. And then I will use the Fermi-Golden rule to calculate 1 over transport pretending that I know the correlation function here. And for the time being, I'll just say that this is some correlation function W of Q. Well, how Fermi-Goldman rule works. You have an integral. Let's say we're in 3D, we're in nickel. So I have dqq squared. The integral is limited by 2kf because that's the maximum momentum at transfer. I need to throw in this transport factor, which in angular form looks like this. But if you rewrite it in terms of momentum transfer, this is q. This is q squared over 2kf squared. This is transfer. Then I have a correlation function. And then I already split my integral over the momentum into the magnitude part. And here I will have the integral over the angles. And it will act on a delta function which conserves energy. Okay. And I will use a fancy annotation for this integral. Just by looking at its units, delta function of energy has units of time. Right? I can call it time. I can call it time. Delta t is a function of q. And for the time being, I don't know what this time is. But if I calculate it, I will find that this is 1 over v Fermi q. 1 over q is distance over the velocity is time. All right. And so what we need to do is to plug in the mean field correlation function and calculate the integral. And if you power count the factors of q, you will see that actually the integral is coming from the upper limit. I have q squared, q4, there is factor of q here, and this is only 1 over q squared. So the main contribution to scattering is coming from short distances, so order of the interatomic distance, which is the same in nickel as the Fermi wavelengths. So they said, okay, fine, this is some constant, boring, uninteresting contribution. It doesn't have any critical dependence. Let's subtract it off and focus on the universal part. And so if you subtract off the boring part, the rest is going to depend on the reduced temperature. I call it theta minus Tc. Tc is mod theta log of 1 over theta. Okay. So this is non-analytic dependence, and this is known as Dijen-Rudel scaling. Any questions about this part?
W, both the short range disorder and the spin fluctuations?
No. So short range is already included into 1 over tau s. I'm only calculating additional contribution due to long range. Oh, if you power count the integral, even with long range contribution, the integral is coming from the upper limit. So you have to subtract this contribution and yeah.
Expression, at least the constant part, exists also at the ferromagnetic side of the transition?
Yeah, so because it's constant as they thought, and this was not right, but they thought that this is non-critical contribution, just in addition to 1 over tau due to disorder. That was their thinking, which was wrong.
But the spin fluctuations, the short range spin fluctuations contribute at both sides of the transition.
Yeah, but they don't have singular dependence. Yeah. Yeah, so we're only looking for a singular part. Yes. I'm sorry. Oh, this is the spin correlation function, for which I'm using the mean field form, but the only thing that I need from this form is to see that at large Q, the integral is still coming from the upper limit. And then, of course, once I learn this, I cannot use this form. I have to pretend that I know the exact correlation function which works at all Qs. This is only for distances much longer than the atomic spacing. Yeah, this is from here. Oh, I'm sorry, I skipped one step. Yes, of course, it comes as a dependence on the correlation length, but the correlation length scales as 1 over mod theta 1/2. You substitute it here, and you get the. So it's kind of same thing. Psi or reduced temperature, they are transformable into each other.
Singularity is coming mainly from that correlation.
It's coming from Q of order psi minus 1, or in real space, distances of order the correlation length, which is long range near the phase transition. 10 of 10. Anything else?
How do you get the
Sorry? Well, it's a constant in the sense that it's not function of theta.
Oh,
Everything else is certainly there.
so it's
Constant doesn't mean that's a number, right? So it's just theta independent part.
it still depends on.
Well, it depends on everything. Yes. All right. 10 years later, two other giants, Michael Fisher and James Langer, revisited the same problem. And boy, they found lots of problems with this. One was kind of obvious, is that Dijen-Pridel scaling contradicted the experiment, at least known at that time. Think about this. Their prediction was that the resistivity has a cusp. The resistivity has a cusp. If I differentiate over the reduced temperature, it will take one factor of theta out. I will have a divergence in the temperature derivative of the resistance. There is no cusp in the resistivity, at least that was the data known by that time. The cusp in the derivative of the resistance. Okay. So if I do d rho dt, I will see this. But rho by itself is a monotonically increasing function through the transition. Okay. So that didn't work. Then they all, and that was really big insight, which was not appreciated at the time, is that although it seemed to be very natural to add up two scattering rates, there is a condition one can do it. And this condition is not satisfied near the phase transition. Namely, if I have mean free path due to short range disorder, and I have a correlation length, right? I can treat these two scatterings as independent if the mean free path is much shorter, is much longer than the correlation length. Okay. In this case, let's say this is a scattering event at long range disorder. It's kind of smooth. The change of the momentum is small, real space and momentum space. So change of the momentum is of order 1 over psi, right? And I don't know about short range impurities if the region in which I have this change in the momentum is shorter than the mean free path. In other words, long range scattering occurs without any information or interference with short range scattering. Okay? But obviously, this is not going to be the case near the transition because the short range mean free path stays are constant, and the correlation length diverges, and it's going to be the other way around. Okay? And one can call this regime ballistic with respect to short range. And there is an opposite regime, which is diffusive, when the mean free path is much shorter than a correlation length. And one obvious effect which is coming from here is that electron has many, many short-range scattering events by the time it completes one small long-range event. And that means that its special function is already smeared by short-range antidisorder, right? Okay. The Fermi-Golden rule here has a delta function here. If you think where this is coming from, it's coming from the integral over time, where you assume that the state has a sharp energy, right? So if the states don't have sharp energies, we have to replace this delta function by something like a Lorentzian of the width 1 over tau due to short range. They didn't do it. I mean, Adjan and Friedel. It was done later by other people in various combinations. So you replace this by something like this, or look at several models. But the main argument that Fisher and Uplanger rolled out was that the assumption that the short range part of this integral is non-acritical is incorrect. Why is it incorrect? Well, the momentum integral here is essentially the same as the integral for the internal energy of a magnet. You also have to integrate spin-spin correlation function over Q, and the integral is always coming from the upper limit. But by that time, of course, especially to Michael Fisher, it was known that specific heat beyond mean field level does have a critical dependence on the reduced temperature with index alpha. And that means that because C of T is du dt, the same behavior as we see in the specific heat should show up in the temperature dependence of the resistivity. It's coming from the same range. This is known as Fisher-Langer scaling. And it does correspond to data on nickel and cobalt, because there is a cusp in the derivative, is theta to minus alpha. However, if I integrate this cusp over, I will have a monotonically increasing function within E. Right? And till mid-70s, I guess, the belief was that Fisher and Lee, yes.
Why should zero dt behave in the same manner as dut?
Okay. They rho and u behave in the same way because they are controlled by the integrals of the correlation function, which is in itself are controlled by upper limit or short distances. So proportionality constant is not known, right? But the fact that it is C specific heat, which is divergent, right, identifies d rho dt with C. So I think if you ask anyone who is working with magnets, resistivity anomaly, they will tell you that Fisher and Lee is the thing. Until you start to look at some other data, and data has become better already in the mid-70s, and started to look like, first of all, even in nickel, if you get very close to the transition, then you start to see some peak, which was not there on the scale back in 1932. And then if you extend your treatment to bimetallic magnets, rare earth magnets, then you start to see something different. You start to see kinks in, peaks in the resistivity, or peaks and kinks in the resistivity. So the geography becomes very wide. And what I'm going to claim is that Fisher and Langer was certainly right. And there is always this R contribution which is coming from short distances. It's there, sacrosanct. However, the fix of the long range part, which consists in replacing the delta function by Lorentzian, is incomplete. It doesn't capture the main issue of a diffusion, which sets in this regime. And lo and behold, if you do it properly, which you do with diagrams first, just to be on the safe side, then you find that there is a long range R contribution, which is stronger than Fisher and Lee one, at least for the common type of the universalities we can think of. O3, Ising, in 3D and 2D, right? How they are compete, it depends on the prefactors, right? So that we don't know, but presumably these deviations from the observed Fisher-Lee scaling, this is coming from the correct treatment of the diffusion part of the long range R contribution. Okay, so do it very quickly next time. I'm out of time, obviously. Questions? Yes, Steve.
Sorry, just